Power-driven machinery generates massive, unforgiving physical force. Maintaining industrial safety requires the active management of these vectors, treating human caution as a secondary defense. For decades, factories operated on a reactive mindset. If someone gets hurt, tell the next person to be more cautious. But humans are inherently fallible. The modern approach treats a factory floor as a complex technical problem, requiring a strict framework of systems engineering. Engineers use a fault tree analysis diagram to map how mechanical failures and accidents occur. By tracing a potential accident down through operational faults, we isolate the root cause, designing physical countermeasures that break the chain of events before human contact. To engineer that kind of fail-safe environment, we have to strip machines down to their basic physics. We must strictly categorize the specific vectors of a mechanical hazard to build a hierarchy of physical safeguards. This systematic approach accounts for the raw mechanics of the environment, removing the requirement for human perfection from the safety equation. Machine hazards break down into a strict kinematic taxonomy. The first major category is crushing, which occurs anytime two hard surfaces progressively move together. This diagram illustrates a squeeze point. It happens when linear motion pushes an object against a fixed surface. You see this constantly, like an automated robotic arm or a descending scissor lift, creating zones where heavy force intersects with static walls. The second crushing subtype relies on rotary motion. These are called run-in or knit points. This schematic shows an in-running knit point, where rotating objects come together, drawing material inward. Power transmission elements create these hazards, like where a belt meets a pulley, a chain meshes with a sprocket, or a rack meets a pinion. The physics of a knit point are brutal. Because rotation continuously feeds material forward, it pulls loose clothing, hair, or limbs deeper into the mechanism. The constant inward friction makes self-rescue nearly impossible, resulting in severe tissue damage. The final primary hazard category relies on cutting rather than crushing. This is shearing. Shearing involves power-driven blades designed to slice through high-density materials like metal, plastics, and industrial composites. If an operator reaches under that descending blade to place material or make an adjustment, the machine will process a human hand with the exact same ease it processes sheet steel. Correctly identifying whether a machine crushes, nips, or shears is the strict first step. Without isolating the exact kinematic action, you cannot design an effective physical countermeasure. Once the type of force is categorized, the engineer has to map the machine geographically to locate exactly where that force is concentrated. In safety terminology, the most critical zone is known as the point of operation. This is the precise location where the machine's tool physically engages the workpiece. This standard metal lathe has a complex system with dozens of moving parts and overlapping hazard zones, but the cutting action itself happens right here, where the chuck spins the metal. That is the exact point of operation. Statistically, the vast majority of all severe machine injuries occur exactly at this point of operation. The concept applies universally to any equipment, whether turning steel or drilling down through a heavy plate. The spot where the tool meets the material is the epicenter of risk. Secondary hazards like power transmission belts at the back of the machine or flying metal chips certainly require guarding. But they don't demand the constant close-quarters interaction that the tool interface does. The point of operation often carries a hidden, specific danger: intermittent motion. Unlike a continuously spinning gear, intermittent tools sit completely motionless for parts of the production cycle. This static state tricks human muscle memory. An operator becomes comfortable, forgets the hazard is live, and the machine unexpectedly actuates to clamp. Because the point of operation requires a human to load material close to the hazard, it demands the highest density of engineered protection. Safeguarding is the process of physically and systemically decoupling the human operator from those identified hazards. The baseline defense is a fixed barrier or a die enclosure. These are static physical guards bolted to machines that deny anatomical access to the danger point. But static guards have a major vulnerability. Operators seeking speed can unbolt or remove them, restoring the hazard. To solve this, engineers step up the hierarchy to use interlocks. An interlock is the critical bridge between a physical barrier and the machine's internal electrical logic. If a worker tries opening an interlocked guard, a switch trips and instantly disables the mechanism. The machine cannot physically cycle while the barrier is out of place. Moving further up the safety hierarchy brings us to dynamic devices, like the presence-sensing light curtains used on heavy industrial presses. Instead of a physical wall, the machine projects an invisible, solid-state laser grid across the hazard access point. The moment a solid object breaks the beam, the control system fires and the heavy press ram freezes mid-stroke. These active devices do not physically block the operator. They rely entirely on sensors to cut power and stop the mechanical cycle. By responding at the speed of light, dynamic devices optimize factory workflow while preventing human-machine kinematic intersection during standard operation. Yet, physical guards and light curtains share one critical limitation. They are only designed to protect operators during normal, highly predictable production cycles. The most catastrophic industrial accidents rarely occur during routine work. They happen during maintenance, adjustments, or when clearing a material jam. Bypassing normal safety systems for maintenance requires an entirely different operational protocol, achieving a zero mechanical state. Achieving a zero mechanical state requires the verifiable neutralization of every energy source, including the residual forces that persist after the main power is disconnected. Even with the electricity severed, a machine remains lethal. High-pressure pneumatic lines can still fire. Compressed springs hold hundreds of pounds of tension. And large rotating components store massive amounts of residual kinetic energy in their flywheels that can take minutes to safely dissipate. Isolating and verifying that every single energy source is dead is strictly enforced through lockout-tagout, or LOTO protocols. Physical locks are applied to the breakers and valves, so the machine cannot be restarted while a technician is exposed. Failing to properly train on these isolation procedures leads to millions of dollars in OSHA penalties every year. Industrial safety is never an accident. It is a continuous, rigidly engineered system, one that maps out kinematic forces, installs localized dynamic barriers, and enforces an absolute zero-energy baseline before a human hand ever touches the machine.